Hello everyone, welcome to our channel. In the Donuts series we saw how to fine-tune pre-trained model for multiple visual document understanding tasks. The model was pre-trained on pseudo-reading task, just like OCR, to read text in the image in correct order. But what if we want to extract more than raw text from physical documents, for example tables, codes and formulas? Or you want to ask questions on documents? OCR won't take us too far, and here's an example. These PDF documents are extracted using OCR-based solutions and contains extracted words that doesn't make sense at all. In this video we are going to explore a better alternative than pure OCR-based solutions. So this is Dolphin, a vision language model capable of parsing complex document images. It's trained on analyze-then-parse approach. In first stage, the model finds out reading order and bounding boxes for each element type. In the second stage, these elements are fed into model, in parallel, along with type-specific prompts. Its architecture is identical to Donut. If you haven't checked out that series yet, you can watch for detailed explanation. It uses Swin transformer as encoder and Embart decoder with expanded vocabulary and longer sequence length. Here's the demo space. It can parse a diverse set of elements from documents. The parsed table is actually wrong because it's the initial release of the model. We'll use recent version of the model that has better parsing accuracy. Now let's quickly see how it does all of these. Document image is first scaled to fixed size, while maintaining aspect ratio, and then converted to tensor. Image tensor goes into encoder to produce the hidden states. Text is tokenized and encoded. The decoder then uses these hidden states via cross-attention to generate result autoregressively. Dolphin parses document in 2 stages. In first stage, we prompt it to parse reading order of the document. Then it figures out bounding boxes for each element. If it's an image, we exclude it from next stage. Rest of the elements are passed again to the model, in a batch for parallel processing. Each element has its own type-specific prompt, for example, parse the table in the image. In the paper, they mostly used synthetic data for pre-training. The model was trained to pair related elements together. They implemented a model identical to Donut, but the decoder has 10 layers. They also mention the learning rate used. For fine-tuning, we should use lower than that. Effective batch size may seem large, but it's nothing compared to 30 million samples. They used square images for training. Initial model was trained with normalized coordinates. Model could parse content if you ask for specific bounding box region. The authors also mention the limitations of the model. Like the model only supports horizontal text flow, it's bilingual and doesn't support handwritten documents. Initial model was trained on 15 element types. And here's the list of type-specific prompt used during training. The model was initialized using pre-trained Donut model, and was instruction tuned. Here are some training examples. Last month, an updated version of the model was released, with improved parsing capabilities and additional element types. They've provided inference code, but we're gonna see the entire pipeline of parsing document images in Google Colab. We will also use custom functions than those provided in GitHub. Apart from block-level elements, the model also parse newlines, subscripted and superscripted text. These normalized coordinates are not used anymore. There isn't a clear mention of what changed in latest version, so we have to look for it manually. The model feels a bit slower because of additional transformer layers and expanded vocab. Given that the model is rich text parser, that shouldn't be a concern. Since pre-training doesn't have handwritten documents, it fails in parsing handwritten notes. Notice I'm using Donut Processor. To generate in batch, prompts need to be formatted in specific format. Padding is required for batch inputs. Since we've added special tokens manually, we don't need to add them. Images are converted to tensors. Attention mask for ignoring padding tokens. When decoding we keep all special tokens, then we manually remove prompt, padding and EOS token. These are the images to test. Let's define minimum functions, required to parse documents using model. Each element has its own instruction prompt. We keep image dimension when scaling, so that we can later crop from original image. This way we can feed high-resolution images to the model in second stage. This function just create a padded square image, as mentioned in the paper. We first scale the longest dimension to target size. Next, we calculate another dimension, while maintaining same aspect ratio. We keep scaling information. Here's how this function works. We scale the image to fit on square image, then paste it on top, left corner. This simplifies our bounding box calculations, as the model now predicts coordinates within the range of resized image. To crop from original image, we can multiply predicted coordinates with scaled values we saved earlier. This parse layout string function is very similar to string to JSON function in Donut model. Here we are scaling the predicted coordinates to be able to crop from original image. In first stage, we parse layout of the document. Since the image is vertical, padding is added on horizontal dimension to make it square image. Here's the result of layout parsing prompt. We have coordinates and element type. Let's visualize these predictions. Now for stage 2, we send these recognized elements to the model in a batch. But first, let's check our coordinate scaling function. These are coordinates on resized image. Once we scale these up, we can crop from original image. We filter out images from stage 2. Along with cropped image, we append type-specific prompt. We now have grouped images and corresponding prompts together. We're predicting with batch size of 4. We parse cropped images and prompts to generate content. Note that these prompts result in parsed text content and not coordinates. We keep reading order, element type, and text content. Finally, we combine images and parsed content and rearrange them based on their reading order. Model has failed to parse copyright symbol. Let's parse another document. It's really impressive that model keeps line break. Model can also parse list. Table is parsed as HTML. Model can't parse icons, emojis and sometimes special characters. Superscripted text is parsed in this format. You can further process these combined results to HTML or Markdown. If the model doesn't perform well on your document images, you can easily fine-tune the model for your specific use case if you've watched our donut playlist. If you liked this video, don't forget to subscribe to the channel. Thanks for watching. See you in next one.